Good morning, everybody. Today we will continue the quantum gases, the specific example that we started last week. Let me find it. Okay. So just remind you what we obtained. The problem was we have a three-level system. This is our energies. So we have epsilon 1, epsilon 2, and epsilon 3. And the idea was to use grand canonical ensemble. Grand canonical ensemble. Which means that we have a specific mu, mechanical potential, and specific beta, which is 1 over k Boltzmann T. Now, the idea is not to look on independent particles. We don't care about particles because the number of particles is not conserved the moment that we are treating everything with grand canonical ensemble. The number of particles can change, and it actually defines state. Each state is defined by Ni and Pi, okay, instead of just the energy, also the number of particles defines state. And what we managed to obtain is the general partition function for the grand canonical ensemble. But the idea was not to look on given particles or independent particles. What we're looking on is the independence of states, right? Energetic states. Each state does not care if any other state is occupied or not occupied. Particles interact. States, they do not interact. Okay? And what we obtain is that for each given state, and when I'm telling you state is the energetic state, but also the spin, you can say, well, but the spin, there are two spins, up and down, and the energies are independent of the orientation of the spin, but for me it's just different states, so I count them differently. Okay? So for each given state, the partition function is that z epsilon I, for example with state up, was 1 plus e to the power minus beta epsilon I minus mu. Okay. Now we're dealing here with fermions. This is the harsh constraint that each state can be occupied either by 0 particles or 1 particle. Now you see that indeed it is independent of the orientation of spin. Therefore, the grand canonical partition function z was z epsilon 1 up, z epsilon 1 down, z epsilon 2 up, z epsilon 2 down, z epsilon 3 up, z epsilon 3 down. Okay. So in total, what we obtained is that the partition function was 1 plus e to the power minus beta epsilon 1 minus mu to the power 2. Why? Because the degeneracy of the spin, 1 plus e to the power minus beta epsilon 2 minus mu to the power of 2, and 1 plus e to the power of mu minus beta epsilon 3 minus mu to the power of 2. Okay. Now, the moment that we have the partition function, all the thermodynamic quantities are obtained by using the thermodynamical potential that is associated with the grand canonical ensemble. And we know what is the grand thermodynamical potential that associated with the grand canonical ensemble. It is the Legendre transformation of the energy E minus Ts minus mu n. Our coordinates become T and mu instead of S and N. Okay? And this is the grand canonical potential. So there is the partition function, there is the grand canonical potential, and the connection between those two is psi equals minus 1 over beta log of z. Okay. Now you have those three. You have the microscopical details in terms of what is epsilon 1, epsilon 2. You have the states and the temperature in beta. You have the chemical potential in mu, and you should get everything out of those three equations. Now, we stopped at the point that before going and computing what is the average number of particles in the system, what is the average energy in the system, etc., 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 we want to compute a very specific quantity that is going to be very useful later, which is the occupation probability. Probability of energetic level I. Okay. The question is, I'm looking, for example, on the energy level epsilon 2. It is not the specific state over here of the whole system, but a very specific energetic level. And I'm asking what is the probability that I will find there a particle. Okay, so the energetic level I, and usually I also should write down whether I'm looking on specific spin up or spin down. So for example, let's consider the spin up. All right, so how I'm computing this? Because several students asked me specifically about this computation that we performed the last minutes of the class. I will repeat it. So the question is as follows. I want a specific probability that there is a particle with spin, for example, up, sitting at epsilon 2. Okay. Great. What do I know and how I should compute this probability? I know that a probability of a state, a given probability of a state, is giving me how. So the state for me, remember, the state of the system is not the specific state of a specific energetic level. The state of the system is, I'm looking on the system and I'm asking, all right, what are the different occupations of the different levels? And I have to look on the whole different levels, right? So when I'm asking a state, okay, let's consider it's a vector, okay? And this is epsilon 1 with up. This entrance is epsilon 1 with down. This entrance is epsilon 2 with up. This entrance is epsilon 2 with down. This entrance is epsilon 3 with up. And this entrance is epsilon 3 with down. What do I mean by entrance? So consider that I have a vector. Okay. And in this vector there is 1, 2, 3, 4, 5, 6 different places. And for each place, I'm writing either 0 or 1. Okay? So for example, 1, 0, 1, 1, 0, 0, it's a specific state of a system for which there is a particle, fermion, at level epsilon, energetic level epsilon 1 with spin up. There is no particle at epsilon 1 at spin down. There is one particle at epsilon 2 with spin up. There is one particle at epsilon 2 with spin down. There is no particles at all at level epsilon 3, disregarding the spin. Okay? So this is a specific state of the system. When I'm asking about occupation probability of the energetic levels, I have to consider all the different vectors, okay, for which I don't really care what happens at the first two places. I don't really care about the three other places. The only thing that I care about is what is sitting at this place. Okay? So the only thing that is important for me if I'm asking occupation probability for energetic level epsilon 2 with spin up, I have to look on all the different states for which here I have 1, 1, 1, etc., etc., etc. I have to count all the different states, okay, compute the probability for each different state, okay, and sum all those probabilities because those are different realizations of my system, right? Now, why do I have to compute the probability of the whole system, of the whole state, right? Because this is what grand canonical ensemble was designed for, right? If you remember, if I have a canonical ensemble or grand canonical ensemble, the probability of any given state, Fi, when I'm writing here Fi, the probability of a state, I mean the probability of one of those, right? Of a system to be in state I, and this is one of those states, Fi equals 1 over z e to the power minus beta epsilon I minus mu n I. This is the probability. Okay. So I know how to compute probabilities and the occupation probability, right, by computing those guys. Z, I know what z is. EI and I also know. Why? Because, well, I look on the state, for example, this one. I'm saying, okay, so what's the energy of this state? The energy of this state, I have epsilon 1, contribution 1, epsilon 2, contribution 2, and epsilon 3, contribution 0. So EI, for this specific case, is what? Is epsilon 1 plus 2 epsilon 2. And Ni, it is 1 plus 2 plus 0. Okay. I substitute those numbers into this equation and I obtain the probability. Right? That's it. Now, this is not enough. Why it's not enough? Because you see, I have different states that contribute exactly to this occupation probability. This state contributes to the occupation probability that epsilon 2 with spin up is occupied. This state also contributes to the probability that energetic state epsilon 2 with spin up is occupied, etc., 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 etc. Okay? So I have the probability, occupation probability equals to sum over all relevant I, okay, 1 over z e to the power minus beta epsilon I minus mu n I. This is the occupation probability. I have, first of all, according to the basic laws of probability, define or look on how my probability is defined. This is how my probability is defined. Now associate with each probability a specific outcome and count all the possible outcomes that are relevant to my question. My question is occupation probability of specific energetic level. Great. Now,
if you have an integer spin like 0, 1, minus 1.
So that is what I have here. This is what I hear. Here
No.
I have plus 0. No,
here I have
it's not fermion. We'll deal with bosons later.
Okay.
All right. The idea is going to be very, very similar, but it's bosons, and the Pauli exclusion principle is not present.
Mm-hmm.
Okay. All right. Now, so what is this? This guy involves, because of the epsilon I, mu I, and how it's represented by different indices or different entrances of this vector, it's actually not a regular probability. It is a joint probability. Right? Because it's a joint probability of energetic state epsilon 1 and epsilon 2 and epsilon 3. So this is joint probability. Joint probability. In Hebrew, הסתברות משותפת, או התפלגות משותפת. Okay? Now, I'm not interested Why I have to sum those up? What is the summation? Remember first year probability class. I'm interested in the regular probability, right? Singular probability. התפלגות שולית. How I'm going from joint probability to regular probability, I sum up over all the possible states of everybody else except the only guy that I'm interested in. Okay? This is why the summation. Now, there is a general statement that applies to independent random variables. I remind you, if I have x1 and x2 random variables, and I want to compute the probability density function, or the probability function of random variable x1, and I have a mutual or joint probability function of x1, x2, x1, x2, okay? What I do, and this is what I performed over here, I sum up over all the different values of x2 of the joint probability x1, x2, x1, x2. This is why I'm summing up over here, and this is why mathematically it works, and we proved it, or at least I proved it to some of you in my class 2 years ago. All right, now, so we sum them up, we have this probability, yes, we have to sum everything, but there is one exclusion. In the case when x1 and x2 are independent. What happens when they're independent? When they're independent, px1, x2, x1, x2, okay? It is just the multiplication of px1, x2, x1, x2, right? I'm sorry. x1, px2, x2. The probability, the joint probability, okay, of everybody, when everybody are independent, is just the multiplication of the probabilities. Okay, I plug all of this inside. So what I get, px1 of x, I have to sum them up, okay? x1, x2, and I summing over all the different probabilities, x1, x2, x1, x2, out of the summation, okay? I have summation over x2, px1, x1, px2, x2. I don't care. Okay, so the joint, so the regular probability that's coming of the summation is just the single probability of a single state. Okay? px1, x1. What I'm trying to say to you that we have a factorization trick. The factorization trick, it's not a trick. It's a probabilistic idea of saying that everybody are entities. In our case, it's not particles, but energetic levels are independent. So I don't care that I designed this joint probability for a macroscopical system of many different energetic levels. We don't care. The moment that they are independent, we can treat each and single one of them independently. Right? Now, this means that although all of this discussion over here is very much relevant and it's very much important, okay, because this is what exactly you have to do, but the factorization trick, which leads to multiplication, which is independence in probabilistic language, says to you the following. You don't have to calculate the joint probability. You don't have to care about everybody else, right? In the word of Richard Feynman, what do you care about what other people think? You only care about yourself, which is your occupation level. So F occupation probability of epsilon I is going to be 1 over Z epsilon I, we spin up e to the power minus beta epsilon I with spin up minus mu. And that's it. And that's it. Right? You don't have to care about everybody else. Why? Because they're independent. Well, there is a mathematical reason, etc., etc., etc. The factorization trick is not a trick. It's the same as in probability. If you look on almost everything that it's done in probability, advanced probability, regular probability, okay, so there's a lot of large words, and a lot of like mathematicians like, but eventually they operate over independent entities. The same is done over here. We know how to treat independent particles. Yes?
In what situation would you not be able to do to say that the particle states are independent?
For example, if we would try to solve everything not by independence of energetic states, but by the independence of particles. They are not independent because of the Pauli exclusion principle. So everything won't work.
But this is an example where you have, like if you have two particles in the same energy level, you don't have another term that changes the energy according to spin. There's no like fine structure or something.
No. So your perspective have to be very different. The perspective is energetic levels are the entities. They occupy or not occupy. Particles are not the entities. Okay? That's crucial. If you look on the particles, particles are always independent. There is nothing that I can do, okay, in order to break the Pauli exclusion principle. It won't work. But for each level, it doesn't care. Okay? So it's like it's a minor perspective. You think, well, what I care, particles or levels, but it's a huge perspective in terms of independence. Okay?
It's an abstraction you're doing.
Yeah.
Okay.
Eventually, the goal is to solve, right? My goal is to solve something, and not just to say to you, oh, it's very complicated, let's run a simulation, right? So my goal is to solve something and understand something. Okay, so this is the occupation probability. One single energetic level with a specific spin, so we choose a very specific level or state of the system by using energetic level with a specific sets of quantum numbers. Okay? Great. Now let's look how this guy looks like. So we choose a specific energetic level, epsilon, and instead of writing epsilon I will write epsilon. So this f of epsilon, I will omit this occupation probability, and it is e to the power minus beta epsilon minus mu, divided, what is this? 1 plus e to the power minus beta epsilon minus mu. Now notice epsilon is the different energetic levels that I have. I haven't told you what they are. They can be 3, 4 joules, 10,000 joules, 7k volts 1T, etc., etc., etc. So I'm going to vary the energy. Now usually what is prescribed in the grand canonical ensemble, it is the beta and mu. So beta is 1 over k volts 1T, and mu is the chemical potential. Okay. Now instead of writing it like this, you know what? It's like this. I don't care. So this is F. Yes?
What happened to Ni?
What happened to Ni?
Usually we put it in the partition function. Do we assume it's 1?
This is for a single state.
Okay.
What happens to the single state? It's either 0 or 1.
But, okay, so
When it's 0, it's not contributing to the occupation probability. The occupation probability contributing only the realization, where here starts what? 1.
any degeneracy right before has disappeared because of the factorization.
The degeneracy, no. I'm looking on a very specific state. There is no degeneracy.
Got it.
All right? No degeneracy, because I define. I want to look on energetic state. Let's consider epsilon 2 with spin up. Absolutely no degeneracy. It's either occupied, then the number of particles is 0, or unoccupied 0, or occupied 1, and the occupation probability is when I plug here 1. Okay, so this is our F. This is our epsilon. And let's see what happens to this function Let's see what happens to this function. So first of all, I know the following. I know no matter what my temperature is, when epsilon is very, very, very large, okay, so you know what, let's write it even differently. Epsilon equals to 1 over epsilon beta epsilon minus mu plus 1. It's also sometimes called Fermi distribution. For us right now it's not a distribution, it's a probability. There is a difference. But we'll see why it's called Fermi distribution later. Okay. So, when we plotting this guy as a function of epsilon, but we have two parameters, beta and u, okay, which are the temperature of the system and the chemical potential of the system. Now, for very large epsilons, where this guy goes? 0, right? The exponent of something which is extremely large, okay, no matter the mu is constant, okay, we take epsilon to infinity, we have epsilon exponent of something very large plus 1, we don't care about this 1. So for large epsilons, it always goes to 0. Okay. Now what happens for small epsilons? Okay. What happens for very, 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 very small energies? Okay. When energy goes to here, well, it actually depends on the beta. Okay. It actually depends on the beta over here. But if, for example, the energy could be negative, it will go to 1. Right? So if epsilon is very, 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 very large and very, very, very negative, okay, it will go to 1. Okay? So the idea is that it somehow approaches this 1 over here. So this is what we know. Alright, but there is a very special point in the middle. What happens when epsilon equals exactly to mu? Okay? When epsilon equals to exactly to mu, so we have an exponent of beta multiplied by 0, so all of this is 1. Okay? And we have plus 1, and 1 plus 1 is half. So here is the mu, and what we know is that somehow our function have to cross this point, which is exactly 1/2. Okay, so the function looks no, it's bad. It's bad. Okay. This is approximately how the function looks like. Now what we see is the lower the energy is, the higher the occupation probability is. The higher the energy is, the lower the occupation probability is. So, logical, right? It's a physically physical assumption that usually the lower your energy is, the higher the probability that you're going to occupy it, and this is what's exactly what we see over here for each given state. Each given state have epsilon. Now, how this guy is modified when we change t. Okay, so beta, this is a plot for a very specific temperature. Okay, this is a plot for a very specific, but this temperature can be high or low. Okay, now what happens when beta is very, 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 very high? Okay, so for extremely high beta, what happens over here? Do we care if it have epsilon to the minus mu? So that I'm sorry. The temperature is plotted over here, mixed up a little bit. High temperatures, high T. So for high temperature, beta equals 1 over k Boltzmann T goes to 0, right? Beta goes to 0. So when beta goes to 0, epsilon to the power 0 multiplied by something, which I don't really care what the something is just 1. Okay? So for high enough temperatures, the occupation fraction, occupation probability, is almost independent of the epsilon. Okay, so maybe it's a little bit high over here, and it's a little bit lower over here. Okay. But in general, it's almost flat. So we have equal probability to be, no matter what epsilon here it is, we have equal probability of occupation of an energetic state if the temperatures are very, 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 very high. So what do we know? When the temperature is extremely high, the value of the energy of my given state is irrelevant, right? My energy can be very low, or it can be very, very, very high. The occupation probability is always almost 1/2. Okay? Now, why it happens? Because when the temperature is very high, how should I put it? The kinetic energy, which is 1/2 k Boltzmann T, goes to infinity. So the specific energetic state, it's irrelevant because I have very large kinetic energy, so I can occupy any energetic level exactly with the same probability. So this is T goes to infinity. Okay. What happens when T low temperatures? For low temperatures, beta equals 1 over k Boltzmann T goes to infinity. Okay. So here it's a little bit different story. Mu plays a major role over here. So when epsilon, my energy of my given state, is lower than the chemical potential mu, okay, this number, epsilon minus mu, is what? It's negative. So we have epsilon to the power of beta, which is infinity, or something extremely large, multiplied by a negative number. So this is extremely small. So it's 1 divided by something very small plus 1. So it is almost like this.
Oh.
Yes.
Yes, it's like 1.
Yes. Yes. It's almost 1. Okay. What happens for epsilons that are larger, the energies that are larger than the chemical potential? So I have E to the power of something big multiplied to the power of something positive. So here I have, instead of setting a very small number, I'm going to have a very large number. I don't care about 1, so 1 divided by something extremely large is almost 0. I have this. Okay? So this function now tells me the following. If your energy of the state that you're looking on, this epsilon, when you're looking in the limit of low temperatures, if the energy is lower than this mu, the probability that this state is going to be occupied is exactly 1. Okay? But if the energy of your state is higher than this mu, okay, the probability that your state is going to be occupied is exactly 0. Okay? This mu, in the limit of these low temperatures, have a specific name. It's called Fermi level. And what we know is that all the states, all the energies below the mu Fermi are occupied because the occupation probability is 1, and all the states that are above mu Fermi are unoccupied. Okay, so you now want to look on the different energetic levels of the system, and you look on this function. By the way, the people who learn here at AI know this function. It's called the sigmoid function. And this is exactly how the different neurons in neural networks operate. You have a little different entrances, and the system defines it's going to put outside a 1 a voltage or 0 based on this function. So all the AI networks somehow operating on this Fermi. For us it's irrelevant, but it's very, very relevant to other systems. Yes? Have a question? No. Okay. So, two very simple basic limits of occupation. Low energies, the only thing that matters is mu Fermi. You're below mu Fermi, the probability that I will find there a particle is always 1. I'm above mu Fermi, the probability that I find a particle over there is always 0. High temperatures, okay, mu Fermi is irrelevant. Any state have exactly the same occupation probability, which is 1/2. Okay. Somewhere in between, I have not high temperatures, not low temperatures, green temperatures. Okay, I will have something that looks like this. It have to decay to 0. It have to decay to 0, right? But well, depends on exactly what's the level of the temperature. What is the temperature your temperature is. Now this Fermi distribution, okay, this dependent on this function, is very, very, very important to any system where there are fermions. Pauli exclusion principle. Because what you're going to do in the next class, we are going to do in the next tomorrow, we're going to operate with this function even for systems where there are interactions. Why? Because explicitly at the level of low temperatures, you see you don't care about anything. The only thing that matters is your mu Fermi. Okay? That's the only thing that matters. Now you can say, but Stas, they're interacting somehow, they're pushing somehow, etc., etc., etc. The only thing that matters is the Pauli exclusion principle, and what we will see is that this mu Fermi is very strong. So your low temperatures, the number of particles can be huge, it can be large, and think that every state is occupied up to some specific mu Fermi. Well, it may be a little bit unclear, I will repeat myself tomorrow, but this guy, this object, Fermi distribution, defines all the properties, the regular properties of electrons in metals. And we will see something about that tomorrow. Thank you. לפני מה?
שלב לפני שזה עובר לפונקציה תטא.
כן, 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 כמובן, אתה עובד באיזשהו גבול, אתה אומר בסדר, יש לך טווח דינמי עד שאתה מגיע, והטווח הדינמי הוא בערך מסדר גודל של קייל בולצמנטי, כי זה דורך כמו 1 חלקי קייל בולצמנטי, אז יש לך טווח דינמי, כל מה שזה אומר, אתה לא חייב להגיע לתת הפונקציה.
בתור איזשהו אחד וקו ומשהו נהיה רגע.
לא, אתה אומר, אתה פחות יכול להגיד רגע פה, כן, התחום הזה הוא 2 קייל בולצמנטי, פה אתה עובד, זה רק אומר לך איפה אתה עובד מסביב לפרמי, אתה לא חייב ללכת לתחומים, לטמפרטורות מאוד מאוד נמוכות, אתה יכול להגיד כל הזמן אתה עובד פה.
אוקיי, רק שאלה אחת, כל מתרגלים משהו לשבת האנרגיה, אם הסכימה לתת...
אז אם לא ראיתם את זה בתרגול, ולא ראיתם את זה בהרצאה, תלכו למתרגל ותגידו להם, לא למדנו.
לא, זה ממש הצד של הגרף, זה נגיע לזה.
אוקיי.
לא, אז צריך לעצב אותה.
לא, זה לא בעיה.
שאלה
בעיה.
כן.
זה בעיה קשה. לא, אחד סביר, השני נוראי.
זה המיו.
זה המיו
אני
שלו.
לא יודע כמו לומד.
אז למה דווקא כשהאנרגיה גדולה ממנו?